So welcome everyone again to our statistics seminar series. So today we have the pleasure of having Vasilis Syrgkanis. Vasilis is an assistant professor in management science and engineering, and by courtesy in computer science and electrical engineering in the School of Engineering at Stanford University. He's also affiliated with the Institute of Computational and Mathematical Engineering, an active member of the Stanford Operations Research Group, Statistical Machine Learning Group, CS Theory Group, and the Stanford AI Lab, and other labs. So Vasilis has broad interests in symptomatic inference theory, causal inference, and today he's going to talk about source condition and double reverse inference. Yeah, and then we're going to have until 4:30. So Vasilis said that he's okay with questions during, so we can take a time and you can just ask. And you don't need to worry about the Zoom. I'm going to be monitoring Zoom.
Okay.
So yeah, take it away.
Cool. Yeah. So thank you very much for inviting me. First of all, great pleasure to present here. So I'll be talking about a problem that is motivated by unobserved confounding and causal inference. So it's an estimation problem that tries to deal with unobserved confounding and causal inference, and we're trying to build sort of like improved estimators for an abstract versions of this problem. So let me just give you some motivating examples before going into the general formulation of the problem that we're going to be addressing. So here's one prototypical example of a causal inference problem. Suppose you're trying to estimate the price elasticity of demand. Typically, you will have that your observed price in observational data is driven by unobserved confounding factors, like local events are going to cause surge in prices. So let's call these local events U. And so when this local event is happening, prices are higher. When the local event is not happening, prices are lower. And typically, you don't observe those local factors. And so if you try to look at the correlation between demand and price, you'll get some erroneous relationship that demand increases with price. How do you solve that? One way to solve such unobserved confounding and causal inference is through the use of instruments. So instruments are variables that affect the treatment assignment, but don't affect the outcome of interest other than through the treatment assignment. So in the case of demand estimation, for instance, people try to look for cost shifters. So try to look for factors that are going to change the cost of production of a product, but they're not going to change. But that cost of production sort of like happens in the production side, doesn't happen in the demand side, and that those cost shifters are independent of demand. And so you would say that I'm going to now parse the data and split them into samples where the cost was high, medium, or low, and then I'm going to fit sort of like project all of my observations into these groups and fit a curve on those averages within the instrument groups. And then if you do that, then you're going to get the right causal relationship. One way to see that in equations is to say that we have this sort of like partially additive outcome equation where we have some nonlinear function of price plus the unobserved confounder plus extra errors, and the price is driven by that unobserved confounder. And we have some cost shifter Z that is independent of the U but affects the price. And if we look at the expected value of the outcome conditional on the instruments, then this is going to be the expected value of that demand function that we're trying to estimate, conditional on the instrument, plus the expected value of that unobserved confounding factor conditional on the instrument. Since the instrument is independent of the latent factor, we can drop that conditioning. And by normalization, let's assume that the unconditional value of that unobserved confounder is 0. So we get that this thing that we observe in the data is a convolution of the thing that we're trying to estimate. It's equal to the expected value of the demand conditional on the instrument. And so we have some sort of like identifying equation for that unobserved demand function, which is an inverse problem that roughly, like this linear system of equations that defines H is equal to that observed quantity. And oftentimes we care about some average summary statistic of that demand function, like the average derivative, which is sort of like an average price elasticity of demand. And so in this situation, we have an inverse problem where this convolution of the function that we care about is equal to some observed function, and we care about a functional of that solution to the inverse problem. Such functionals of linear inverse problems also arise in other ways that people try to deal with unobserved confounding. For instance, many times people assume that you have, even though you don't observe that unobserved confounder, you have proxies for that unobserved confounder. So you have some proxy that affects the treatment. So these are called the treatment proxies. And you have proxies that affect the outcome. And crucially, the treatment does not directly affect X, and this treatment proxy does not directly affect Y. And if you have such a structure in your data, you manage to identify such treatment proxies and outcome proxies, and you care about understanding what would be the outcome if you intervene and fix the treatment to be equal to 1. So suppose that you were trying to estimate the average potential outcome when we always treat. If we could observe the unobserved confounder, this would be a way to identify that quantity. But if we manage to have such a structure, then we can still formulate this problem as a functional of a linear inverse problem. And in particular, if we make the extra assumption that this outcome proxy is sufficiently correlated with the confounder, such that we can write that conditional expectation of Y given U and D as the convolution of some function of only X and D, then the quantity of interest can be identified as the average value of that function evaluated at D is equal to 1. And this function can be also equivalently be phrased as the solution to a feasible instrumental variable regression problem or in linear inverse problem, where the instruments are the treatment proxy and the treatment, and the treatments are the outcome proxy and the treatment. So I cannot, I don't have the time to go into the identification, how you improve this identification strategy, but this is just to show you yet another example that is also starting to be more and more used in causal inference that leads to, again, the same type of statistical problem where I care about some functional of a function that is defined as the solution to a linear inverse problem. So this is the type of statistical problem we're going to try to address. So we're given NIID samples that contain some variable Z, some variable X, and other variables W. And we want to construct an alpha confidence interval for some average linear functional of an unknown function H0, which is the solution to a linear inverse problem. Okay. Where I can, it's convenient to think of this conditional expectation here as a linear operator applied to the function H equals to some element here, which is another function equals R0. So this is a solution that defines a function, but you can think of it as a linear system of where a matrix T multiplies H equals to R0. It's just that this matrix T is infinite dimensional. And this R0 here is a regression function. So the two problems that are the two motivating problems are special cases of this more general formulation. And in fact, we're gonna, for the sake of generality, we're actually gonna think of even more slight generalization of this problem, where this element R0 over here is not necessarily a regression function, but is what's known as the solution to a Riesz representer problem. So it corresponds to the Riesz representer of yet another linear functional M tilde, meaning that you have another linear functional, and that linear functional has this inner product representation where R0 is that element that allows you to specify the linear functional as an inner product. And for the special case where M tilde takes this very simple form, the Riesz representer is that regression. That's the most general setting that we're going to analyze. But for the sake of, if you want to think about a concrete problem, it's easier to think of R0 as being a regression function. So let me first begin because I guess let me give an overview of the main result, and then I'll try to go into its in more detail of what are the elements that lead to this main result. So the first observation is that under some regularity assumptions, the parameter of interest that we care about can actually be phrased as the solution to a dual problem that takes the exact same form. So the parameter of interest here is the linear functional of a linear inverse problem, where R0 is the representative of that linear functional. We can equivalently phrase that parameter as this linear functional evaluated at the solution of a dual inverse problem, where now the treatment becomes the instrument and the instrument becomes the treatment. Okay. And this A0 is the representative of that original linear function. So there are two ways that you can express the same parameter. And it's just that one solves an inverse problem where you have Z as the instrument and X as the treatment, and the other solves another inverse problem where X is the instrument and Z is the treatment. These two dual representations also allow you to also formulate a doubly robust representation, where you take the first representation, you add the second representation, and then you subtract something that is in between these two, which is basically the inner product of that solution H0 with Q0. So that you can show that this representation has doubly robust properties, meaning that as long as you estimate H0 or Q0 correctly, this is going to give you an accurate estimate of the parameter of interest. So then that lends itself to an estimation strategy where you go and solve the primal inverse problem. You estimate it, you give an H hat. You solve the dual inverse problem. You estimate it, you get an Q hat. Maybe you do that on a separate sample. And then you go to a first sample and you calculate an empirical average of that doubly robust representation. And applying standard results, you can get that this estimate is going to be asymptotically normal, and you can construct confidence intervals. As long as the product of the errors in your dual solution and in your primal solution converges to 0 at rates that are faster than 1/10. So we either need to be able to estimate the primal accurately or the dual inverse problem accurately. So then what we want is to be able to construct estimators such that this product of the rates converges to 0 at faster than 1/10. The problem is that solving linear inverse problems is statistically very hard, primarily due to the ill-posedness of the problem. So we're trying to invert an infinite dimensional matrix, and we have a sampled version of that matrix and a sampled version of the target on the other hand side of the equation, right? So we're solving an infinite dimensional linear system where we have errors both in T and R0, and so this inverting that linear system can be very unstable in practice. What matters in how well you can solve this linear inverse problem is, for instance, how well is that solution, the true solution, is it primarily supported, or does it primarily span the top part of the spectrum of that infinite dimensional matrix? Okay, so that's a property of the problem that guides how well you can actually solve this problem. And one way that you can formalize and quantify that intuition is by a property called the beta source condition of the linear inverse problem. So the beta source condition is a quantification of how much the true solution of that inverse problem spans the top part of the spectrum of that operator T. And the larger the beta, the easier the problem, the more well posed. So the more it is supported on the top part of the spectrum. But of course, the beta source condition is an assumption that we need to place on our problem. It's a non-testable assumption. And so it's obvious that the less we assume, the better. So the more we can relax that beta source condition, the better, the more robust our estimation strategy will be. And it's also hard to know which of the two problems, whether the primal or the dual problem, is going to be more well posed. So we have two ways of estimating that parameter of interest, either solving the primal correctly or the dual correctly. How well we can solve the primal or the dual depends on that unknown beta source condition. And so, how can we relax our requirements and have a more robust estimation strategy? So this leads us to the main question we wanted to address in this paper, which is, can we devise an inference strategy that guarantees asymptotic normality for the target parameter if either the primal or the dual source condition is sufficiently large without knowing which one is the largest one? Right? So without knowing which of the two inverse problems is more well posed, can we estimate our target parameter leveraging the more well posed of the two ones without knowing its identity? So that was and so the reason why we wanted to address that question is because at least it removes one of our assumptions. We need to assume that one of the two inverse problems is sufficiently well posed, but we don't need to assume which one of the two is the more well posed one. That's why it leads to
Sorry, question. What would be a situation where you wouldn't know which one is better posed? Because like in the previous slide, you just said that like the dimensionality of the beta is directly proportional to how well posed this problem is. Could you maybe...
I'm saying so the beta source condition is an assumption about the true quantity and how much it spans the top part of the eigenspectrum. It's something that you need to assume, right? It's something that you say, okay, I believe that my problem satisfies that beta source condition, but it's not something that you can measure from the data. And so the main result is that we can actually do that there exists an estimation strategy that allows you to leverage the more well posed of the two without knowing which one it is. And we can also do that even when the linear inverse problems have multiple solutions. So even when you don't have uniqueness of the inverse problems, even though we will make an assumption that implies uniqueness of the target parameter. Even when the inverse problems have multiple solutions, there is an assumption that you can make that implies that the target parameter is uniquely defined. Okay. And in particular, what we will, like the main result that we will show in picture is that if you follow the estimation strategy that we described, and the estimation strategy is going to involve function spaces. So you're going to assume that your primal solution lies in some hypothesis space, your dual solution lies in some other hypothesis space, and you're going to need to measure the statistical complexity of those hypothesis spaces. We're going to use the notion of the critical radius to measure the statistical complexity of those hypothesis spaces. And then we're going to have an estimation strategy that says that we get asymptotic normality as long as that critical radius does not sort of decays to zero faster than n to the minus alpha. So these are not too large of hypothesis spaces. And that alpha over here is upper bounding relates to the maximum of the source conditions using this figure, as this figure describes. So let me parse out what this figure says. So over here on the x-axis, we have the more well-posed of the two, so how well-posed they are. As beta grows to infinity, then basically we're as if we're solving a regression problem, not a linear inverse problem. And so as beta goes to infinity, we need that the critical radius basically goes down to zero faster than n to the minus 1/4, which is what you would require if you were interested in functionals of regression functions, not of functionals of linear inverse problems. So that's the beta go to infinity. If your beta goes to zero, then you require that the models that you're assuming be parametric. So you need that the critical radius is at 1/√10. So you cannot deal with richer than parametric function spaces. And so as beta grows, you're allowing yourself to go from parametric spaces to non-parametric function spaces, albeit it has to be that their statistical complexity is still of the order of, cannot be like slower than n to the -1/4, which is what you would even require in the case of functionals of regression.
Can I ask a question?
Yeah.
If beta goes to 0, then you're supported on the bad part of T,
Yes.
on the wiggly part.
Mm.
But then you're making at the same time the assumption that the solution needs to be in a parametric model. How do you know that that parametric model will contain that very wiggly function? That solution that is very wiggly.
Yeah, that is a thought indeed. Yeah, so I would say that this beta equals 0 is sort of like an irrelevant
But
result.
even closer to that,
Closer to
you're still.
Yeah,
Isn't there a tension between the two?
both of them, I guess, are free. I would say are free parameters because it could be that because the beta source, it could be that they have the same eigenspace, but one has the operator has eigenvalues on the lower part, and the H0 has eigenvalues on the upper part. So they could be in the same
So
sort of
if
like.
beta goes to 0, the eigenvalues are also on the lower end, right? I mean, they are over the entire spectrum.
Yes.
So
Um,
anyways, I don't
yeah,
want to interrupt.
it's a good question. Yeah, so
And I believe, having read your paper, that you don't need to make the assumption on the true, which is the minimum norm solution, actually.
yes.
You actually need to make it on the regularized target only, not on the H naught, but on the H star, which is, so anyways, I just,
That's true.
because that picture was confusing me when I read it.
Yeah, but I agree that the critical radius is I guess the critical radius is an inequality that has to do with the norm of the decay of the norm. So how much? Okay, so suppose they share the same sort of spaces. It could be that H0 is spanned on the lower part, and so it's true that the delta n will. It could be. I guess it could be that like they span. It could be the same basis, but the ordering could be flipped. Like right, so it could be the same basis, but like what has the largest singular value for the operator is what has the smallest singular value for the.
Because at
for
the
the-
end you have a series, so at some
Yeah.
point the eigenvalues have to decay anyway, so
Mhm.
I'm not sure.
Okay.
uh,
And so another thing to point into on this picture is that if we know which of the two problems is more well posed, then we can better adapt to the more well posedness. If we do not know, then we get something that is slightly suboptimal, but sort of like is almost as good as as knowing which of the two ones. So there is some loss in the requirement by knowing or not knowing which of the two problems is more well posed. Okay. So let me now give an overview of the techniques. So first, let me go through that understanding why, under which assumptions we have uniqueness of the parameter, even though we don't have uniqueness of the inverse problems. So first, again, we're going to use this theorem that says that every linear functional has an inner product representation, so that the original linear functional M has some inner product representation A0. And the main assumption we need to make is that that dual inverse problem that tries to use this dual linear operator that uses X as the instrument and Z as the treatment admits a solution. So I said that in the beginning that under some regularity assumption, the two have, there is this dual representation. The regularity assumption is that the dual actually admits a solution. It's not necessarily true that that dual inverse problem will always have a solution. And that's an assumption that we need to make, okay? That this dual inverse problem always admits a solution, which basically is an assumption that this research presenter also lies in, is not supported too much on the lower spectrum of that dual operator. Under this main assumption, then you can show that this dual representation of the target parameter by a simple chain of equalities, where you take the parameter, it is this linear function of H0, which by the Riesz representer theorem is the inner product of A0 and H0, by the fact that A0 is the solution to this linear inverse problem, I can replace A0 with the expectation of Q0 given X. I can then take X outside, and so now I have this intermediate inner product representation between Q0 and H0. I can further now do a tower rule where I take an expectation of H0 given Z, which is exactly equal to that solution of the primal linear inverse problem. And now because of that, this is because R0 is the Riesz representer of the dual functional, this exactly equals to the dual functional at the element Q0. And so this chain of equalities gives rise to both the primal representation that, like inner product representation, and this final representation that is the dual. And then you can also show that if you assume that that dual has a solution, then every solution to the primal inverse problem will give you the same parameter. So even though that linear inverse problems might have many solutions, every solution will give you back the same parameter. And you can see that by saying, let's take an arbitrary solution H to the inverse problem. It has this inner product representation, A0 times H. Again, because A0, the dual has a solution, I can replace A0 with that conditional expectation, which is again this inner product representation between Q0 and H. I can do another tower rule, but now once I do this tower rule, this, because H is a solution of the primal problem, this will give me back R0. So no matter what solution H I have to that primal problem, I will always get something that is independent of that primal solution H. Okay. So no matter what H I plug in here, I always get this quantity. Okay. So for any two H's, you'll still get the same parameter. So that allows us to restrict ourselves to estimating the minimum norm solution to those linear inverse problems. We don't need to assume that those solutions have unique, those inverse problems have unique solutions. It suffices to find the minimum norm solutions to those linear inverse problems. So we can replace our original problem with the extra qualification that says here we want the min norm solution to the primal and the min norm solution to the dual. In the context, for instance, of the proxy controls example, this would be our primal problem, and the dual problem, the Riesz representative of this quantity of this function over here is this inverse propensity that tells you, is my treatment 1 divided by the probability of receiving treatment 1 given X. So that is the Riesz representative of this functional, and so the dual problem asks, can I, can I find the function of the treatment proxy and the treatment, such that when I take an expectation of that conditional on the outcome proxy and the treatment, it gives me back that inverse propensity score. So for that to happen, it needs to be that this sort of inverse propensity score function is sort of like sufficiently well behaved that this inverse solution this inverse problem admits a solution Q. So this is the dual example there. In the case of the average derivative with an instrument in the demand example, this is our original inverse problem, and the dual would be whether there exists a solution Q to this inverse problem where the target is the derivative of the log density of the treatment. Okay. So again, you would need this would essentially impose assumptions on the derivative of the log density of the treatment. So then, once we have these representations, we can, as I said in the beginning, we can take the sum of the first two, subtract the third, and we can get that this sort of like representation of the target parameter has the doubly robust property that if I subtract this for an arbitrary h in q minus the true parameter theta 0, this bias will be equal to the product of the error in h multiplied by the error in q. And that's a very sort of like, it's a simple argument. So then we can take it to an estimation strategy where we split our data in half and we construct estimates of the two inverse problems of the first half, and then we calculate this simple average on the second half. And for the asymptotic normality theorem, we need the following assumptions. We need that both of our estimates converge to zero, sort of like their estimation error converges to zero with respect to the mean squared error metric. So the L2 metric or the mean squared error metric for both estimates converges to zero. And this product of the errors converges to zero at faster than 1 over root n rates. And we also need some other regularity assumption on the functionals that they satisfy what's known as a mean squared continuity property. So then this theorem tells us that we need to devise some estimation strategy such that we have consistency with respect to this mean squared error metric, and we have fast rates for this product of the two errors. An observation from prior work also says that this product of the two errors is basically, you can apply Cauchy-Schwarz inequality, Tower rule and Cauchy-Schwarz inequality in two ways. In the first way, you can first do the Tower rule for the errors in H, and then a Cauchy-Schwarz, which gives you that this product of errors is upper bounded by the product of the mean squared error for the dual inverse problem, multiplied by a weaker metric for the primal. So this is where you first project your errors onto your instrument, and then you take an L2 norm of that. Okay. So this is a much weaker norm than this norm. It's much easier to estimate an H hat with respect to this norm than to this norm. You can also do the same thing in the other way. First do a Tower law with respect to X, and then do a Cauchy-Schwarz. And then you're going to get this weak metric for the Q function and the strong mean squared error metric for the H function. So that says that what we need for asymptotic normality is to have some estimation strategy such that both functions are consistent at any rate with respect to the strong L2 metric, and such that either we get like fast rates for the dual with respect to the strong metric and weak metric rates for the primal, or strong metric rates for the primal and weak metric rates for the dual. So we can choose for which of the two functions we're going to target estimating them with respect to a strong metric or with respect to a weak metric. Again, these are the definitions of these metrics. So now, okay, so this is our task. And we're going to try to basically devise a strategy such that, without knowing which of the two problems is more well posed, we'll be able to say that the minimum of these two quantities goes to zero faster than 1 over root n. And the hardness is that if you can very easily achieve weak metric rates without any sort of like regularization. But if you want to get strong metric rates, you need to add regularization. So you need, in some sense, to choose for which of your two functions are you going to add the regularization. And choosing for which of the two functions to add the regularization, you need to know which of the two functions is more or less well posed. But we're going to try to sidestep this requirement that without knowing for which of the two functions is more well posed, we're going to figure out a way to add regularization. So let me first give the more formal definition of the source condition. So the source condition says if let's look at the simplest case where our operator T admits an eigen decomposition. So there is a countable eigen decomposition where sigmas are the singular values and Ui and Vi are orthonormal bases of the two spaces. And we can write both operators in this singular value decomposition form. then what the source condition says is a combination of both the support of the true solution on these basis divided by the decay of the singular values. A more simple way to internalize this is that the support of that function h on the lower part of the spectrum, so for any m, the support of h on all the eigenfunctions below m is upper bounded by sigma m to the 2 beta. So as beta goes to infinity, basically this says that after some m, the support is going to be 0. So and as beta goes to 0, then we're allowing this tail support to be a constant for all m. And another way you can actually, and maybe slightly more intuitive property is that you can phrase the beta source condition as a source condition for the target quantities. So instead of stating as a source condition for the solutions to the primal and the dual, you can also frame them as a source condition for the quantities on the right-hand side. So either the Riesz representer of the dual or the Riesz representer of the primal functional needs to lie on the upper part of the spectrum of these operators. Okay, so that's another way of phrasing. So we need to be arguing about whether the conditional expectation of y given x or that inverse propensity lies on is a more smooth function. So either whether this is a more well-behaved function or this is a more well-behaved function, or similarly, is this a more well-behaved function or this a more well-behaved function? So that's what the source condition is asking us. So we're going to try now to devise an estimation strategy that guarantees that the minimum of these two ways to do the causes-Farts inequality goes to 0 at the facet and 1 over root n rate, so long as the maximum of the two source condition, either beta for the primal or beta star for the dual, is larger than some quantity. So this brings us to how we're going to actually estimate those inverse problems via Tikhonov regularized adversarial estimators. So since both problems are basically of the same form, let's focus on estimating the primal. Finding solutions to linear inverse problems has a long history in econometrics and statistics. In particular for the case where this R0 is a conditional expectation, this problem is known as the non-parametric instrumental variable regression problem, and there's a long line of work that gives ways of estimating non-parametric instrumental variables. Roughly speaking, the approaches that are being used is either approximate your function using some linear sieve, and then apply a sieve 2SLS approach, or a sieve minimum distance approach, where you try to minimize that minimum distance quantity, that minimum distance criterion, where h is approximated by a linear function, and then these features t conditional on z is also approximated by yet another linear function. So both expected y given z and expected phi given z are approximated by linear functions and growing the sieve appropriately. And another approach that has been used is actually approximating the operator itself, so estimating via kernel density estimation, approximating that conditional density of the treatment given the instrument, and then using, again, the same minimum distance criterion together with a L2 or Tikhonov regularization, and solving, plugging in these estimates of the two operators and solving for h. We're going to try to avoid sieve, try to allow for non-linear function approximation, and we're also going to try to avoid explicitly estimating conditional densities. And also we're going to try to generalize to solving not just NPIV, but solutions to those more generalized linear inverse problems where the target is a Riesz representer and not necessarily a conditional expectation. So we're also going to try to at the population limit, we're gonna still try to minimize the minimum distance criterion. So we know that we want TH to be equal to R0, so we're gonna minimize over H that minimum distance. But the question is, how do we turn this minimum distance into something that is empirical and some empirical criterion on the samples? The first observation is that you can turn this minimum distance criterion into a maximum of some risk, right? So you're taking a maximum over test functions Q. These test functions are trying to find, like regions of Z where this H does not match R0. Right? So Q is trying to identify regions where TH is not equal to R0. And we also need to penalize Q so that it doesn't abruptly jump when H is close to R0. So that's one intuition, but if you do the math, you can see that this maximization problem will have a solution that is equal to the minimum distance criterion. So that's the first observation. And then the second observation is that what we get from this adversarial characterization is a product of R0, which we do not know, multiplied by Q. But by the risk representative property of R0, R0 times Q is exactly the dual functional evaluated at Q. And so even though we don't know R0, we don't really need to estimate it first. We can simply plug in here the evaluation of that dual functional at Q. And so this relates to this idea of automatic debiasing. This is a way of doing automatic debiasing for this general setting of functionals of linear inverse problems. So this is our population criterion now. It's equivalent to this population criterion. But now we can easily turn this population criterion into an empirical criterion by replacing that expectation with an empirical average. So now we're going to minimize over our hypothesis space the worst case such violation, but now the violation we're going to measure with respect to an empirical average as opposed to expectation. So that's the adversarial approach. If you just solve this adversarial approach using roughly an analysis that's similar to a prior work where we looked at just a non-parametric IV problem, you can show that simply solving this adversarial approach achieves an error rate for the weak metric of the order of delta n, where delta n is that statistical complexity of the hypothesis space H relates to the statistical complexity of the hypothesis space for H and Q. So you can show weak metric rates without any regularization. But if you want to actually estimate H hat with respect to the strong metric, you need to add Tikhon of regularization that penalizes solutions with a very large L2 norm. Okay, so you need to add that Tikhon. You need to approximate the Tikhon of regularized population criterion. And you can do that empirically by simply adding that empirical L2 norm of the target hypothesis H. So this is going to be our final empirical estimation strategy. And lambda is a regularization parameter that should be tuned depending on the beta source condition to achieve a small, strong metric rate. So here's like a formal version of the theorem. Assume that the true nuisance function lies in some hypothesis space, and that differences between projected differences of that hypothesis space subtracted minus the true H0 lie in some other hypothesis space Q. So this we're sort of like in a realizable setting where we know flexible enough hypothesis spaces that contain the true function and also projections of differences of those functions when you take an expected value of those functions given the instrument.
Sorry, what is H, little h?
Little h is any the space that we're optimizing over. So we're optimizing over hypothesis space H, and we also know that projections of any element of that space, of course, centered around H0, lies in some other space Q. So we need to assume that we fix those H and Q. we are going to assume that all random variables and functions are absolutely bounded, and that the dual moment satisfies the same mean squared continuity property that we needed for asymptotic normality. And then delta n will be the critical radius of the product function space of products between h and q, and the critical radius of the composition of functions in q with the moment. So these are the function spaces for which you need to control their critical radius. Then you can get that the Tikhonov regularized adversarial estimator satisfies that it achieves a strong metric rate, which depends on the regularization parameter in this form. So you have a leading term, which is like the sample complexity of those spaces divided by the regularization, plus a bias term that goes to 0 if beta goes to infinity. And it also achieves weak metric rate that whose leading term doesn't actually depend on the regularization. And you also have a bias term that is going to be non-zero when you add regularization. So what you need to read from these two parts is that if you want to optimize for that weak metric rate, you should basically set lambda to 0. If you want to optimize for the strong metric rate, you should balance your lambda. So you should choose your lambda to balance the variance part and the bias part. And you should choose it in a manner that depends on that beta in the source condition. So depending on which convergence metric you care about, you have a different choice of an optimal lambda. This is all of it. No, this is like you're optimizing over H in capital H. Yeah. So H is the space that you're with respect to which you're solving that. So if we want a very fast strong metric rate, then we need to choose lambda to be roughly of this form, like 1 over 1 plus beta. And we get this rate that is not delta n squared. It's slower than delta n squared. If our function classes were parametric, delta n squared, delta n would be roughly 1 over root n. And so we will get a mean squared error of 1 over n, which is a fast rate. But here we're not going to get delta n squared. We're not going to get a rate of 1 over n. We're going to get something that is roughly beta over 1 plus beta. And with such a choice of delta n, if the beta source condition is satisfied, then you also get a weak metric rate of delta n squared. So it's true that if it happened that the source condition is satisfied, then for that optimal choice of lambda over here, you're actually going to get a delta n squared over here, if the beta source condition is satisfied. But if the beta source condition is not satisfied, then the weak metric rate is suboptimal. You don't get delta n squared, you get something that's slower. So then, if we are trying to understand, so what lambda should we set for the primal inverse problem, and what lambda should we set for the dual inverse problem? If all we know is that one of the two problems satisfies the beta source condition, and we know nothing about the other, then if we choose this optimal lambda for both of them, then for one of them, we're going to get a weak metric rate that's quite slow because the beta source condition is violated for that one. And so somehow we need to know which of the two is the more well posed in order to be able to choose for which of the two we're going to use this optimal choice of lambda. However, we saw that there is, you can change slightly your estimation strategy to be able to get sort of the best of both worlds, where you first, instead of optimizing over all H in your hypothesis space, you constrain your hypothesis space such that this empirical loss function, the max over Q, is not very far from the minimum of this loss function, where the loss function is the unregularized one. So you try to restrict your space such that your unregularized criterion is not very far from the minimum unregularized criterion. And within that constrained space, you optimize the regularized criterion. So adding this extra constraint allows you to get both a fast rate for the weak metric rate and a fast rate for the strong metric rate and a fast rate for the weak metric rate, even if the beta source condition is violated. So this extra constraint over here sort of guards against, like choosing solutions that are very bad with respect to the weak rate, with respect to the weak metric. That's sort of like the main finding in this work, I would say. Because once you have that solution, once you have an estimator that simultaneously allows you to get the best for the strong metric and the best for the weak metric, then you should just choose that estimator for both the primal and the dual. And so if you choose that estimator for both the primal and the dual, even though you don't know whether the beta source condition is violated or not, you're still going to get a fast rate for the weak metric and the optimal rate for the strong metric. And so for whichever of the two like scenarios the beta source condition is satisfied, you can apply the previous theorem and you're going to get that the weak metric is going to get delta n and the strong metric is going to get that beta over 1 plus beta rate. Right? So you get the sort of like the best that you could have achieved without knowing which of the two satisfies the beta source condition. The other thing is that this rate over here has a clipping at 1, so it does not adapt to very large values of beta. So if your inverse problem is very well posed, then you will not be able to leverage that using this solution. To do that, you need to iterate your Tikhonov regularized strategy, where you estimate a solution and then you center the regularization around that solution and you re-estimate, and then you center the regularization around that solution and you re-estimate, and you repeat that many times. And if you do that, then you can actually get the result I presented you can adapt to large values of beta. So you can get faster and faster rates as beta goes to infinity. And with that result, you get our main source condition double or bust theorem. That's it. I'm gonna stop here. If people want to stay afterwards, then we can go over some proof schemes. Thank you very much.
Do we have time for questions? Okay.
In the constrained optimization problem, is mu just a constant? Or is mu going to 0 a certain way?
Yeah, mu, we choose it so that we know that the true H0 is contained in that ball. Yeah.
And as long as the true H0 is in that ball, that's enough.
Yes.
Which doesn't even have to like go to, there's nothing like you're localizing, you're just getting rid of infinite solutions.
Yes.
Extremely.
If I recall, it will be something like delta n squared. Mu will depend on delta n.
Okay.
Yeah.
So when you say you adapt, you still need to know what is, you still need to know the beta max of
Yeah.
the two. But could you devise a theorem that really adapts in the sense that?
Good question. So one thing that it's not in the public version, but we're adding, it's like, basically, if you care about asymptotic normality, there is some, and you fix the delta n, you fix the hypothesis spaces you're working with. There is a largest beta that you need. There's a minimum beta that you need, and so choose the lambda for that, and that and that works.
Right.
So in some sense, that is what you need to choose, and if your delta n satisfies, if you're right, so if
I'm still troubled by the question that I asked you earlier, because
Yeah.
you fix the class and then you find the beta, but that beta implies that the H naught is in that class. and that H naught may be too wiggly to be in that class. Like if I said, my delta n was non-parametric, then I can choose beta max 0, basically. Sorry, the delta, so my class was parametric, okay? Then I can choose essentially beta max 0, okay? But I cannot really choose that because that assumes that the solution is very, very wiggly. It has supports on in an entire spectrum, and your theorems assume that solution is in the class. You see what I'm saying?
Yeah.
So to me, there is a tension there.
Yeah, I mean, we can discuss more, I guess, more offline, but like the one thing that maybe is also interesting to think about is that the source condition is about the true parameter H0, not about the whole space. It's just about one point in that space.
Yeah.
So it's an assumption about one point in that space H.
That is a function, that is one function that is incredibly wiggly, okay?
H0, it could be.
H0.
Yes.
And that has to be in the class. I mean, I'm just
Yeah.
playing the game that
Yeah.
you just indicated. You first give me the class, you find the delta n, you then find. So suppose that I give you the class that is parametric. Now you will
Yes.
say, oh, I can choose beta max 0, okay? And I will say, no, but remember that you also have to make the assumption that H0, your solution, which you now
But-
tell me that it's super wiggly,
Yeah.
is in that class,
Yeah, even for parametric functions, like the source condition will also depend on how strong your instrument is, right?
Mhm.
So like it could be that it's parametric, but like my instrument like barely correlates with that feature of that parametric function space. So it could be that you're very ill posed even when you're parametric, right?
Right.
So that's why I'm saying that the two are, maybe one is more believable with the other, but they're really independent assumptions. I feel like, the one has to do with also the strength of the instrument, and the other has to do really with the, with the complexity of the function. So you could have like a very ill-posed problem even when you have smooth functions, just because the instrument is going to erase some part of that simple function space. It's going to not correlate well with that part of the function space. Right? That's all.
Okay, guys, we have time for one quick question, otherwise we can end. Okay, so let's thank Vasilis again. Let's see the main idea. The question is very
Thanks for the presentation. It was very cool to see an inverse problem in stats. That hasn't been inverse problem statistics have been more recently been hard. So since the 90s, there hasn't been very much work on it. I was wondering if you had though thought about the other problems in statistics besides probabilities that may frame that in whether the approach here can be used for that. So for example,
I have not thought about it, maybe, yeah, but I have not thought about it.
okay, maybe something to keep in mind would be that this is a problem that is an active research area in Bayesian statistics. Because it's specifically in birth phase.